We'll give it another minute or so till it's on time.
I think they just started the video.
I don't.
No, we
Yeah,
don't care.
I think we are ready.
Okay, Cindy wants me to go. Okay, so welcome to today's colloquium, where it's our pleasure to have Khanh Kieu, one of our own professors, who's going to tell us about his work on ultrafast lasers. And to give you some background about Khanh, he got his undergraduate degree and master's degree from actually a sister institution, if you will, in St. Petersburg in Russia. They go by the name ITMO now, just shortened from Institute of Technology, Mechanics and Optics, an institute that's been around for 100 years, started by the czars. And in fact, we're trying to get a collaboration. We've been working on, the Russians invented the word bureaucracy. The University of Arizona has refined it. And so we're trying to work on a collaboration with them now involving a master's degree program. Khanh actually got his Ph.D. working for Massoud, and what most people don't know, that when he first came with Massoud with his proposal for what he wanted to do for his research, it had nothing to do with lasers. And Massoud's reaction to that...
If I were creating a world, I wouldn't have started with butterflies and daffodils. I would have started with lasers. 8 o'clock, day one.
So with that, Khanh left and put together an experiment on lasers, and this is his first laser that he made. And as you'll see, subsequently, he's worked on refining this to go into faster and faster lasers, and we're going to hear today about his work on ultrafast lasers. And so, with that, Professor Khanh. Professor Kieu.
Thank you so much for the kind introduction. Since it's remind me of the war that we had with the U.S. and Vietnam War, recently there's a series in CBS, right, on the war. So and I was born in Vietnam myself, and I'm the first after-war generation. So the war ended in '75. And I was born '76, so I'm very lucky. So during the war, so my house was close to a rice field like this. So during the war, you would see bomb crater like this. Right? So these are freshly made by the B-52 bombers. Right? I was lucky enough when I was born; those would become something like this. Right? So I call this free swimming pool. So I got the first benefit of the war, I guess. So when I was small growing up, I would go out to the rice field and catch grasshopper, fish, and frogs and all of that, and we would go and swim in here. Fish didn't live in these craters for some reason. So only the leeches, right? So before swimming, what we do, you take a stick and you stir the water, and the leeches would come, and you get them off the water, and you can come in and swim. And, very nice swimming pool, clean water, and so. When I look at this, I feel very lucky and fortunate to be here, talking to you about ultrashort optical pulses. It has been a long way from the bomb crater to here I am, and what I want to say is that peace time is great, so we should keep that. Right? So let me start my talk on ultrashort optical pulses here, and I hope I can convince you that in optics sometimes short is good, right? So I'm not very tall, so so this is what Feynman said. There's plenty room at the bottom, right? What he meant was when you go down in size, as you go down into the nanometer scale, you would see smaller and smaller things, and there are more and more interesting things down there, and there are a lot of important applications. So right now, I don't have to convince you that that's true, right? When you go down in space, you go down to the molecular level, and you go down to the atomic level. There are a lot of interesting things, and a lot of interesting technology. So what I would like to convince you today is that as you go down in time now, right, you go to shorter and shorter time scale, there's in a lot of room and a lot of interesting applications as well. Okay, so right now, if you are on the second time scale, I would like you to switch to femtosecond now, right? So 1 femtosecond is 10 to minus 15 seconds. So this is 1 second, right? So if you put it in the normal perspective, then if you take 1 femtosecond to be 1 second, then 1 second would become about 32 million years or so. So we're talking about very, very short and very, very brief moments in time, right? So right now, I think we have conquered the femtosecond time scale already, and people are working actively on other second time scale, and going shorter and shorter, right, to zeptosecond. And the shortest one the next abbreviation that I have seen is 10 to minus 24, right? So anybody know what's that called? The octo, yeah. So that seems to be the limit right now that we have, at least in the language term, right? So it seems to me like every 30 years we go 3 orders of magnitude. So maybe right now we are at the other second range. Maybe in 30 years, 60 years, maybe we can get to this range. Okay. So I would like to point out that as we go down in time, there are, or in space as well, there are a lot of interesting things that can happen. So in this scale here, you can see going from a second to other second and going to zeptosecond. So ultra short punches we call, or ultrafast, is in this range right here. It's about 1 or 10 picosecond or smaller. Right? So that basically that's what we are working in. So below this range right now. And when you go down in time, you start to see very interesting physics, right? So optical fluorescence, for example, that in the nanosecond. If you go to the molecular rotation, like Raman, for example, that in the picosecond, and then when you go down, you see molecular vibration. When you go down to other second range, and you see electron motion dynamic, right? The outer, and if you go deeper inside the atom, you see faster and faster thing as you go down here. So there's a lot of interesting physics as you go to shorter and shorter time. And there are actually many important applications as well. So I have a long list here, a lot of interesting application in material processing, for example. So this show if you use a femtosecond laser to do material removal or ablation, you get better result. Right? The cut or the hole that you drill look cleaner because it's the so-called non-thermal ablation process. Right? You don't create a lot of heat when you use femtosecond laser. With a nanosecond laser, things get more messy because of thermal effects. And there are a lot of other applications here in nonlinear microscopy, in frequency column, in nonlinear optics, and in telecommunication. Right? So in telecommunication, as you go to shorter and shorter bit of information, you can pack more information, right, as you send it. So hopefully I have convinced you that this is something interesting that we should look into. So this is another observation that I just want to bring up. So here, for example, if you look at a molecule, so the size of the molecule is about a nanometer or so. So it would take about 3 arcseconds for light to travel through that distance, right, 1 nanometer, right? So if I define a constant here, you just take the period, so that's 1 picosecond, that's the oscillation or the rotation period, and you divide by the time of flight, then you get about this number 3 multiplied by 10 power 5 or so. Right? So now if you look at the Earth, for example, that's rotating around the sun, right? You take the period that 1 year, right? It takes 1 year to go around the sun, and then it takes about 8 minutes 20 seconds for light to go from the sun here, right? So if you take the ratio, somehow it's come down to almost the same number. So if you think of the Earth and the sun as a molecule, so that seems to work that way. And if you look at other systems, the ratio is in this range. So I don't know if there's any deep physics behind that or not, but there are a lot of young students here. Maybe one of you guys can figure that out someday. Okay, so the general trend is that as you go to smaller and smaller things, the dynamic or the time scale of that system becomes faster and faster. Right? So that why we need to have shorter and shorter optical ponces to study these systems. Okay. So now the next question: how to generate ultra-short optical ponces? Right? You know, we know that's interesting and important. Now the next question: how can we get those? Right? So the simplest and the easiest thing is to take a CW laser and you put a fast shutter. Right? You can turn it on and off that laser very fast. You can form these short optical ponces that coming out, right? Because it's that, you know, turn on and off the laser very fast. So that's the standard technique that we use nowadays for optical communication to optical fibers, right? You have a CW laser and you just modulate the data on top of the laser beam that way. But with this, we are limited by the speed of the electronics, right? And that is larger than 10 picosecond. And also we have large jitter, right? So the ponces are not located at the exact time where they're supposed to be. So there's some big error there. So the second technique that we can use is to put that modulator inside the laser cavity, right? So in the laser you have an active medium, you have the pump, and you have the cavity to have the laser fin to build up inside, or the cavity mode. So now if you just turn it on and off very fast, then you can make a Q-shaped laser, right? And those generate ponces in the nanosecond range, so it's not really short. If you do it right, so if you time this gate open and close, that would match the cavity round trip time. Then you can have a mode of operation where we call that active mode locking, and this laser can now generate picosecond ponces as well, directly from a laser. But you have to time it, right? So you open and close the gate in good agreement with the cavity round trip time. Then you can get the laser to work. But still, with this technique, you still get more than 10 picosecond, and then there's a large timing jitter as well. Okay, so these are still not, by my definition, still not ultra-short or ultra-fast ponces. The way that we're doing it now is a so-called passive mode locking, right? So you also have a laser with that three components that I mentioned earlier. Now what you do, you add in a schedule absorber. This is a very special device or nonlinear device that have interesting behavior. That when you increase the intensity going to it, the absorption is reduced, right? So the higher the intensity of the fin, the smaller the absorption that device has. And another characteristic that is important is that when the electron absorbs the photon, it doesn't sit in the excited state very long. It has to go down right away. So it typically goes down in the picosecond or sub-picosecond range, right? So when you put this schedule absorber in the laser cavity, you basically force the laser mode to oscillate in phase, right? So you can consider each laser mode, each longitudinal laser mode is as a Koshy function. If you think of the fin, the E fin, right? So there's a bunch of Koshy function in there, and because of the schedule absorber, this Koshy function would light up in phase at one brief moment in time here. So when you add these things up, so this would add up coherently, right, in phase, right? So these would be hours of phase. So you would form a short optical ponce that way, and as the output you get a ponce train, right? Because it's repetitive to the cavity round trip. So that and this is the ways that we can get ultra-short optical responses out, and typically a point train, right? And the distance between them would be the cavity round trip time that we have. So this technique is a most popular technique that we use in our lab to generate the ultra-short or ultra-fast optical responses. As a result, we get femtosecond or picosecond that would be emitted at the output. And the benefit also is that the peak power is increased by about 1 million times or more, right? Because when you add up these film together, at this moment in time, you have huge photon density, and at the other moment, you don't have anything. So you can think of a CW laser. You take the gate, and you just squeeze a photon into one brief moment in time. So that's why the photon density very high at that place. Okay, so that is a very brief mentioning about how we do the mode locking. So when you have a mode lock laser, there are actually more laser modes that oscillate in the cavity. So this is from a book that I show you. If you just add, let's say 5 Cosy function, then you get a point like this. If you get 50, then you get a huge point here, and then there's nothing in between, right? And in our laser, typically there would be about 100,000 to about 1 million modes that oscillate at the same time. So if you add like 1 million Cosy function together, you get really, really short points, right? So that is how we get these points generated. Okay, so there's some interesting facts about mode lock lasers that I would like to point out, and there are important applications that comes out of this, except this one, right? So mode lock laser do not work most of the time, right? That is rare that something does not work most of the time and would be that useful, right? I told my graduate student all the time like that. If you want to be useful, you have to work all the time. Don't learn that aspect from the mode lock laser, but it's useful because when it works, it does extraordinary things, right? If you can do that, you can play video game all the time, but when you work, you get a Nobel Prize or something, then that's good, right? So when this comes from the duty cycle, here the duration of the points is about 100 femtosecond, and the distance between them is about 10 nanosecond. Right? So most of the time, if you put a power meter here, you don't see any light coming out. Only very brief moment in time you see that, and then these mode lock lasers generate the highest peak power among lasers. So as I mentioned, you squeeze a photon into a very short burst here. So that's why the photon density is really high, right? When it comes out, and these can reach many terawatt. So mode lock laser provide one of the shortest events in nature. So we can get 100 femtosecond directly from our laser if we design that carefully enough, right? So and this is so short that you can't really get it with electronics, right? So that's much faster than any oscilloscope or detector that we have nowadays to measure this. And then mode lock laser are one of the best frequency rulers, right? So the frequency comm application, they use this laser mode as a ruler to measure frequency, or you can use that to measure time, right? So right now, optical clock using frequency comms is the most precise one, right? They could get down to 10 to minus 19 precision already. And then an interesting property of mode lock laser is that the jitter is really small. We have shown that the jitter of these points that coming out of the laser is less than a femtosecond, right? The distance is 10 nanosecond plus minus 1 femtosecond, right? So it's really, if you think of this as heartbeats, this is the steadiest that you can imagine. And there's a lot of application because of that property. Yeah, okay. So there are a lot of mode lock lasers that you can buy nowadays. So this is a very popular one, that femtosecond tie-shaft laser, and this is widely tunable in that range. And then if you add an OPO, you can extend the tuning range broadly. But the problem when I started working in the laser is that the TISAP laser is quite expensive and bulky, and it requires some maintenance from time to time. So it's difficult to move out of research labs. So there are a lot of applications, but then your laser source is complex and expensive. So it's difficult to get the technologies that we develop in the lab outside into the real world. So that's why we have decided to use optical fiber instead, right? So in optical fiber, you can view a laser by just splicing this fiber component together, and you can just coil them, and you can put it into a small box. And this fiber laser can have quite high efficiency. We have lasers that can have 80%, for example, in optics to optic conversion efficiency. And this can be compact, right? Because you can fold the cavity into a small box like this, and there's no alignment. So when you splice this component together, the light is kept inside the core of the optical fiber, and it doesn't get out, so you don't have to do any alignment there. And then that's why it's reliable, right? So there's no misalignment. And it's low cost as well, because this optical fiber can be pulled kilometer at a time, so you can view a lot of lasers that way. So the challenges that we have to deal with all the time is high power operation. How can we get a lot of power out of this optical fiber? The core is 10 micron or less, right? So now if you want to put a lot of power in it, there's a lot of problems that we have to solve. And also mode locking, how you put the static absorber in, and how you integrate that into the cavity, so that when you turn on the pump laser, you get ultra-short optical pulses out. So there are some solution that we've been working on, so new punch shaping mechanism. So we design the cavity so that the punch evolve in a certain way that it will sustain very high energy, for example, or high power at the output. We developed new type static absorber to do the mode locking task as well. And right now I think we have a very good solution already. So if you look at ultra-fast fiber laser technologies, then there are a few established wavelength, right? So this around 1 micron, that based on the terbium dope fiber, you can get quite high power, over 100 nanojoules. And then based on erbium dope fiber here, also quite good. And nowadays people are now working actively in thulium and holmium dope fiber laser, working at around 1.9, 2 micron. And then we have some at 2.8 micron or so. In the visible, there's some, but really low power, right? So the main message here is that there are still a lot of wavelength gaps, right? That we need to fill with fiber technology. So that means there's still a lot of work to do. For example, right now we are trying to develop laser at 1.3 micron, for example, right here for deep tissue imaging. Right now there's no good solution out there. Or right now 1.7 micron, also for deep tissue imaging, there's no good laser out there that people can use. So since we're working with ultra-fast pulses, the peak power is really high. So they're actually quite a nice solution already to cover these wavelength gaps, right? So, and these are all nonlinear optical processes. So as I mentioned, we have 3 established platforms, right? So ytterbium, erbium, and thulium system. Now if you do supercontinuum generation, for example, and you send a laser beam into a specially designed fiber, you can get very broadband lights that coming out. So that's the experiment I did with TISAP laser. You send in 800 nanometer and you get a rainbow that covers the visible and near IR spectrum that way. So if you do frequency doubling of the erbium or ytterbium, for example, you can get the green laser, and you do frequency doubling again, you can get the deep UV, right? So that one project that we had in the past in the past with Hitachi in Japan. So if you use this laser as a pump to pump OPO, for example, an optical parametric oscillator, then you can get light that at a shorter wavelength and longer wavelength. So these are four-way mixing processes. If you take this and then use Raman generation, then you can shift the laser to longer wavelength. So, or you can take ytterbium laser and you beat that with erbium laser through a different frequency generation process. You just take two lasers, you focus the two on the crystal, and you generate the different interfrequency of the two. Then you can get 3-4 micron light. If you take this system with this system 1.56 and about 2 micron, then you can generate light at about 10 micron or so. So basically, because of these short responses, because of the high peak power, we can have all kind of nonlinear processes that we can use to generate the wavelength that we need. Okay, so all of these interesting processes that we can do all require a mode lock laser, like to start with, right? So, and that what we need to solve first. So the next question is, what is the best approach for mode locking? That's the best approach to generate these femtosecond or picosecond pulses. So there's only 4 main approaches right here. So this curl length mode locks that for tie-sharp laser, and it doesn't work for fiber yet. And for fiber, people has been using nonlinear polarization rotation. So when you design the cavity, you put the wave plate in the cavity, and you set it in a certain way, you can actually create we call it an artificial stereo absorber that would force the laser to emit femtosecond pulses out. Or CSAM, so these are semiconductor material that can work as a stereo absorber that you can put inside the laser cavity and force it to mode lock. Right? And these are the relatively new material based on carbon nanotube and graphene, and that's what I was interested in when I was a Massoud student. So I came up with the idea to use an optical fiber taper, and then I put carbon nanotube around it. Right? So that's the standard optical fiber here, 125 micron, and then you heat it up to about 1,000 degrees C, and then you pull the two fiber ends apart, and at the end you get a taper at about a few micron here, and because of the small size, the light inside the core would leak out into the cladding, right? So now if you put the nanotube around it, you can interact with the nanotube. So that's the device that I built when I was a student here. And it's fiber format, right? So light can go in with the fiber, interact with the nanotube, and then go out. So now you just splice that into the cavity. You can make a laser that really compact and small. So we built the first mode lock laser that run by a battery, basically. So that was 10 years ago. So now if we add in an amplifier, so those oscillators emit only like milliwatt type average power, but the peak power is still about 100 watt or kilowatt. But now if you want to improve that power output, then you can add an amplifier here. Then you can get about 100 milliwatt average power already, and you can get less than 100 femtosecond via the tip of the fiber, and then the peak power is over 10 kilowatt. Right? You know, that's the instantaneous power, and that can be battery operated also, and the cost is more than an order of magnitude smaller than the tie-sharp laser. So with this laser system, you can start to do interesting things. So this is an example that I did when I had the system built the first time. You can build the laser and then the amplifier into a small box like this, and then you send it to a high nonlinear fibers, and you can create a supercontinuum, right? So this is the input laser here, and if you increase the power, you can get very broadband from 1 micron to 2 micron system. And if you take this part of the spectrum and then you compress it, you can generate about 10 femtosecond or so. So this is the shortest points that we generate in our lab. People have gone to attosecond range already, but a 10 femtosecond source in this format is still quite interesting for OCT or frequency comb application, for example. So if you want other wavelength, for example, you can take the supercontinuum and then you can use ytterbium dope amplifier, and you can get very high power over 10 watt laser at 1 micron, and you can get close to 100 femtosecond as well. Okay, so these are the new laser system that we are working on, so-called fiber-based optical parametric oscillator. So these are sync pump laser system, and the main goal is to create widely tunable laser source, right, to cover the gaps that I mentioned earlier. So the working principle is based on four-way mixing. So you have two pump photon interacting with the fiber, and you generate a signal photon on the short wavelength side and then the idler photon on the long wavelength side. So basically you just need to sync the term of the OPO with the pump laser, and you can generate these widely tunable sources. So these are very good result that we got, widely tunable source in the TISA range from 700 to about 900 nanometer, and then the energy and the power and the point duration are quite comparable to what the TISA laser, and it would be a handheld and small format system. So this is the work that we have not published yet, but I think this is in the world record for fiber system right now, and we are using this source for multiphoton imaging. Right? So that's the application of this. So now I want to run through some application of ultra-short optical pulses here. So we have done a lot of work in different area, but today, for the sake of time, I would mention only dual and com spectroscopy and nonlinear optical imaging. So that's the two applications that we are working on actively in the lab right now. Okay, so dual and com spectroscopy is a very interesting technique to measure, absorption spectrum, for example, with very high resolution and very short acquisition time, right? And the technique is similar to Fourier transform spectroscopy. So in Fourier transform spectroscopy, you send the laser source in, and then you split that into two, right? And then you combine them back together, and you change the delay. You get a interferogram, and then you do the Fourier transform. You get a spectrum back, right? So if you put a sample in one arm, then you can get the absorption spectrum that way, right? To the interferogram. So in dual and com technique, you have two mode lock lasers. Here's the local oscillator and the probe. So these lasers emit two femtosecond point trains, but they have slightly different wave rate, right? So in time, if you look at the pulses, then one pulse would run across the other, right? So you basically have a system that does a delay light automatically without any moving part, right? So when you look at this system here, you can get an interferogram that looks like this. And if you Fourier transform this interferogram, you can get the spectrum as well. And depending on the difference in the wave rate here is around kilohertz or so. Then every 1 millisecond you get a spectrum, right? That coming out. So it's very fast. So if you look at the frequency domain, right? So two frequency comb. So you can see the red comb and then the blue comb. If you put the two on the detector, then you can see beating between these comb teeth right here, right? So basically, you down converting the optical domain into the IF domain. So if you measure the signal from the photodiode with the spectrum analyzer, you can get a spectrum, down converted spectrum in the IF domain that way. So the advantages are many. You can get many orders of magnitude improvement in accuracy over the conventional Fourier transform technique, spectroscopy technique, and we can get very high resolution, about 100 megahertz or so. And with conventional Fourier transform spectrometer, you need extremely long delay line, right? And it takes a lot of time to get to this resolution. And the acquisition time is really fast because there's no moving parts at all. The two laser point train would probe one another automatically, right? Because of the difference in the wave rate. But there's some drawbacks that we are trying to solve right now. There's limited spectrum coverage when you generate these femtosecond laser pulses. The bandwidth, the output spectrum of these are narrow, so you can measure quite narrow spectrum at a time, right? So right now we're working on supercontinuum generation to broaden that coverage. It's quite difficult to do dual and com with two separate lasers because you have to phase lock them, right? So you have to stabilize them, so you make sure they have to be coherent with one another. So that's why you need a lot of electronics in there. Our solution is to use the comb that's generated out of the single cavity, and I'll show you in the next slide. So right now, because of this limitation, this comb system or dual comb spectroscopy has been limited. It's used to the lab environment only, because you need all of this complex electronic and servo locking. So these are our ideas that is quite simple, and we published last year if you are interested in more detail. So basically, it's a mode-lock ring laser, and we just take out the isolator so that the laser can laser in both directions, right, clockwise and counterclockwise. And it turned out that we can mode-lock them in both directions. So when they are mode-locked in clockwise and counterclockwise, you can have two femtosecond point train that coming out. And an interesting thing is that these two actually have slightly different rep rate, right, because of the asymmetry in the cavity itself. So now you get two combs that are generated from the same cavity. It's very likely that they will be coherent with regards to one another already, right? So and that's what we did, and we really confirmed that these two are coherent with regard to one another, and we can perform dual comb spectroscopy without any locking or stabilization. So these combs are moving because they are not stabilized, but they're moving together in pair like this. So during the measurement time, they are coherent with each other. So we have shown so that's the interferogram that's coming out from the beating of the two laser point train, and we send that to a hydrogen cyanide gas, and you can see the free induction decay of the gas molecule right due to the laser excitation. And if you take the Fourier transform of this, you would get that's the laser spectrum, and on top of it you would see this very narrow absorption line. And we compare the lines that we measure with the database, right? With the H-tran database, and it's matched almost exactly there. So and each of these, if you see each burst here would be acquired only in 1 millisecond. So basically in a second we get 1,000 spectra or so. So if you do this measurement with an optical spectrum analyzer, for example, it would take a few seconds for one spectrum, right? So with this technique, you can get 3 or 4 orders of magnitude improvement in the acquisition time and also in the resolution. So there are other applications in distance measurement. For example, if you can send these two point train to an object, you can measure the distance to it, right? And a group at NIST actually have done that in 3D, so they can do a 3D kind of mapping of a sample. And then you can use this for temperature sensing, for example. So that's the dual comb. Very briefly about that. And right now we're working to increase this spectrum much further. Right now from 1 to 2 microns. So Neil is working on it. So the next application is nonlinear optical microscopy, and this can work because of the high intensity of the ultrashort laser pulses. So this is showing how it works. So these are the cuvette of fluorescent molecule dye, right? So if you take for 88 nanometer, you focus that down, then you get the fluorescent signal everywhere when you see the laser beam, right? So you see fluorescent all over the place. So now if you focus the femtosecond laser beam down into the cuvette, you see the fluorescent coming out only from very small dots at the focus spot, basically. And the main reason is that this wavelength is below the band gap of that molecule absorption. Only at the focal spot here, the photon density is high enough that the molecule can absorb 2 photons at once, right? And then emit the higher energy photon. So we call this 2 photon absorption fluorescence. So now you can imagine you can take that laser spot and you scan that in 3D, right? You can get a 3D image that way. So that's the multiphoton imaging technique, and you can get very good resolution, diffraction limited resolution, and you can get penetration depth of around 1 or 2 millimeter or so into the tissue, right? So when we started working on this, we realized that the bottleneck of this technique, actually there are two things. The first thing is laser itself, because the Tysab laser is really expensive. It's around 150K or so for a laser like that. And then the microscope is also 200, 300K. So if you want to buy a system like this, it's about $500,000 at least. So it's very difficult to get out into widespread use. So that's a microscope. So these are the codes that we look at, and it's really expensive. So when I started, I said, oh, we can't really buy these, right? We have to build these things, and it turned out that for optics people, it's not a difficult system to build, and I don't know why it's so expensive. So the optical design is very simple, right? You have basically a scan mirror right here that you scan the beam with angle, right? And then you have this telescopic system that you image this mirror into the back aperture of the objective, right, microscope objective, and that objective focuses the light down, and then that's where the nonlinear signals are generated. That's where we detect the signal. So basically, it's a very simple lens system, and we put that two doublet together, and we look at the aberration, and it's pretty good even with 10-degree scanning range, right? So it's not complicated at all, and that's a rendering that Ben Cromie did of the microscope. So basically the laser would come in here, and that's a scanner, and that's the two lenses that I show, and then that's the objective here. And the nonlinear signal from the focal spot would go back here and be detected by these two PMTs. So and then the laser looks like this, and we have some electronics. So the one thing is really compact, and the cost is about 50K only if you build that, right? And a lot of fun that you can get too. So if you can build something and you have time for it, try to build it yourself. It's a good thing. So that's how it looks like in the lab. That's the first version that we have. That's the femtosecond laser, and then that's the scanner up here. So two lenses are in here, and that's the microscope objective, and then these are the two PMT. Basically, if you look at the beam path, right, it's quite simple. So the nonlinear signal would be detected by these two PMTs, and we put filter in front so that we can get second harmonic, we can get third harmonic, or you can get 2-photon excitation fluorescence, we can get 3-photon excitation fluorescence. So a lot of signal that you can get out of this. And then when you have a microscope like this, there's a lot of fun. Really, we've been having a lot of fun in the lab, right? So that's the first microscope that people build, right? When you have something like that, when you look into the microscopic world, you start to see, bacteria, you see onion has layer, for example, you see cell and things like that. A lot of big discovery that has been done, right? When we have access to a microscope. And in my opinion, there's actually another world, right? So not only microscopic world, but there's a nonlinear microscopic world. And we can see that with our multiphoton microscope, right? You get access to that world to our microscope design. So this is an example that Ben did. This is at a microprocessor chip. So it's 16 by 16 millimeter. And basically Ben could map out the whole circuitry of it, right? So and this is basically made of 5,000 individual images, right? So and it took Ben a day or so to do this. So if you zoom in, you can see all the wire and things like that under the microscope itself. So my hope is that maybe we can use this as a tool to assist the manufacturer, right? When they make the chip, they can use this to find defects, for example. Or some of the fun thing that we're trying to do is to maybe look at the circuitry when it's made already, right? So we know the different layers and the different components are on here. So that is an ongoing interesting work that we look at. Another device that I really like is actually a polymer modulator that's made by Bob Norwood group, right? So these are two electrodes, and then the polymer is actually everywhere when they put that in, and then they have to apply voltage across this electrode to pull the polymer, right, to make the molecule to align so that you get the Chi2 response, the second harmonic response. So after that operation is done, you put under the microscope, you see huge second harmonic here, right? So that's where the polymer molecule have been aligned already. They are everywhere, but out here they are not aligned, so you don't see that second harmonic. So on the gold electrode, you see a lot of third harmonics that are in green. So we can use this microscope as a characterization tool for device fabrication. Right? They can see if they have Chi2 response or not, and they can quantify that Chi2. So another thing that we've been working on is to look at 2D material. So these are single atomic layer material, right? Like graphene, for example, that's a single layer of carbon atom, right? So in this case here, we have MOS2. That's a material here. So you can see this is one layer, and this 2 layer, 3 layer, 4 layers, and atomic layer, right? So these are extremely thin material. So if you look at the second harmonic signal, for example, you can see that the signal we get only from odd number layers, right? So this 1 layer, you see the second harmonic. So 3 layer, you see that, and then 7, you see there. So indeed, for second harmonic signal, you need to have broken symmetry, right? Or you need to have odd number of layers. In the third harmonic signal, then the more material you have, the more signal you get, basically. So this is a good tool to study this, the nonlinear optical properties of these 2D materials. Another application that I show here is that came out of Nature Communication is to basically visualize the grain boundary of this material, right? So when they use MCD technique, CVD technique to grow this single layer material, there are a lot of domains, right? And then each domain would have different crystal orientation, right, of the crystal axis. So using our microscope, for example, that's the second harmonic, we can figure out what's the orientation of this crystal axis of this crystalline. So, for example, we have the excitation polarization this way, and we detect that way. Then you see only half of this would give signal. So that means the orientation of the crystal axis for this fleck here perpendicular to that. Right? So, and then on the third harmonic, you can see the grain boundary there very easily. And this image can be done in a second or so. So it's a very fast characterization technique. Okay, so the next thing we try to look into the biological world, right? So that's a lot of interesting thing in there. So the first sample that we look at is actually a leaf, right? So Ben look at this lemon leaf right here, and you can see the red color. That's a chlorophyll filter that we put in here, and then the green one, that's the third harmonic signal. So you can actually map out the chlorophyll distribution in the leaf in 3D with this technique, right? And since we live in Arizona, so we did actually a full mapping of chlorophyll of a mesquite leaf. I don't think it has been done earlier, but I still don't know what's the application of this yet. So it's that for fun right now to look into the nonlinear microscopic world, right, as I mentioned. That now we have the tool to look at. So the next thing is more complex than insects, right? So this is a Drosophila, that's fruit fly sample that we got from the neuroscience department. So basically, you see the Z scan of the image, right? Different Z, and then you put them together, you can create a 3D image like this, right? So remember, we scan the focal spot in 2D, and then we change the Z, we get another 2D image, and we change the Z, we get another 2D image. And at the end, when you put all of these stacked together, right, all these images together, you can reconstruct a 3D rendering of the whole thing here. So that is a part of the fruit fly. Not sure why it's gone, but okay, so the next thing that we have done is to actually look at human tissue now, right? So we look at non-living thing, inorganic things, and we look at the leaf, we look at the insects. So now we're looking at more serious things. So these are sampled from a person already, and this from the esophagus, right? So that's the digestive tract here. So we collaborate with a group in the medical center. So Dr. Banerjee is a gastrologist, so he had patients that complain about the digestive tract, right? So a lot of time he would have to come in and then take biopsies, right? And then so when the biopsy comes out, it would go into the pathologist's office, and then they would slice that into very thin slices, like 4 micron or so, and then they would stain these slices, because if you don't stain, then it looks like transparent. You put under the microscope, you don't see anything. So you put the H&E staining, so that's very popular. Then you start to see the cell nuclei and things like that. And from that information, the pathologist can determine if the person has cancer or not cancer, for example, or other type of disease, right? So it's a long process and a lot of work, right? If you get a millimeter cube sample, right, then 4 micron each, then you can see hundreds of slices, the slice that the pathologists have to look, and it takes a lot of time. So our idea is that, okay, why don't we just take the sample and that put under the microscope and look directly? We don't have to cut into thin slices. We don't have to put the chemicals in. And it turned out that we could see a good third harmonic signal and good second harmonic signal from it. So second harmonic comes from the collagen network of the tissue. So the collagen molecules are elongated, right? So they have broken symmetry. So you get second order nonlinear response. And then in the third harmonic signal, if you zoom in, we can see the nuclei as the black dots in there, right? So when we look at this, the pathologist confirmed that the person has normal biopsy, so no cancer or anything, right? Because all of the cells are lying at their places, right? So very organized, they don't move around yet. So this is another patient that we look at, and this is a huge problem already, because when you look at the third harmonic, you see these nuclei that are moving all over the place already, right? So these cells are highly mobile and invasive already. And then the collagen networks that we think that these collagen networks actually hold the cells in place are destroyed, so that these cells can move around, right? So and that is the state of cancer already, and the pathologists have to tell the doctor to get the bad news to the person, and then they have to come up with a treatment. So with our microscope, instead of very long-term processing, we can just look at it directly, right, without any staining or processing. So right now, Fahad is working on an endoscope, so that we can, instead of taking the tissue out, you can get inside the patient and then look at it directly. It's very difficult, but it's interesting work. So this is another new result that we got. So this is from a mouse already. So this is the pancreas from a mouse, and they grow cancer cell on it, right, to study. And the main goal is to determine the margin where the cancer and the normal tissue is, right? Because in surgery, when the doctor have to do this, he need to know how deep he cut off, right? And right now what they do is that they come in, they film the material, and then they just cut a slide off. And then that would send to pathologists, and then they would take only 3 small locations, only 1% of the surface, and then they would do the slicing, they do the staining, and they look under the microscope, right? So if they see cancer cells, then they tell the doctor, cut more, right? So he cut more, and then the whole process would just repeat like that. So the person would just sit, lie there open, right? And it would take hours to do. So our goal is that to take the tissue and then put under the microscope or endoscope and scan it very fast, right? Without any staining at all. So and that's the result of it. There's no staining whatsoever we put in. That's the tissue fresh out, and you see a lot of colors, right? So you see second harmonic, that's the green color there. So and then 2 photon excitation fluorescent, red, and then we have third harmonic in blue. So as you can see, on the right side, that's the normal tissue, because the doctor recognized all of the structure of the pancreas. But on the left side here, that's the abnormal tissue. It looks a lot bluer, right? You can see there. And now if the doctors get that information, he can just cut about the millimeter away from that. Then the survival rate is a lot higher, right? So that is the ongoing work that we're doing. So the next thing that that I want to mention briefly is in brain imaging. We was working on this, and there's a lot of applications. And the one that I like is to do rapid whole brain imaging, where you get a brain of a mouse, and you can get a 3D image of it very quickly. Right now, it's very difficult. I can tell you why. So right now, so that's the image of a cross section of a mouse brain, right? You can see each of these is a frame right here, and we have to put in maybe 1,000 frames together to get the whole thing. And this whole image took us about 8 hours to take, right? Right, with the current speed. So that means a mouse brain is about a centimeter cube. It would take about 6 months right now if you want to do layer by layer like this, right? So it's been really long. So my hope is that we can reduce that time to about a week or so. And if you can do it less, that's even better, right? So then we can get a 3D rendering of a brain, and then people can study the different processes there. So if you zoom in, you can see the neurons, right? And then all the wiring, the dendrites that connect the neuron together. So it's very, very complex circuitry, but right now we have a technology to map that all out in 3D, right? But right now it takes so much time still. For comparison, there's a standard brute force technique. What people do is they take the brain and then they just slice it into 10 micron each, let's say, and then stain it and then put under the microscope, right? And then you look and you take picture, right? If you do that, one researcher told me it would be about 2 years to get the one brain of about 10 people who work, right? So right now with this we have 6 months, and that's a microscope and one person. So it's been faster, I think. But my hope is that it can go even faster. So if you take the slices and then you make a stack, then you can get a 3D rendering of the signal here. So these are about 250 by 250 and by 200 micron piece. That you can see, and you see the neurons there, and you see the dendrite, right? So my hope is that at some point we can get a whole brain in 3D, right, of a human brain, not only the mouse brain. It would take a lot of memory and data. So these are the last application that I want to mention because this is chemical mapping. So right now, if you have two laser tunable and synchronized, if you tune these two laser wavelengths that the difference would match a Raman vibration, for example, you can map out that signal in a tissue in 3D, right? If you want to look at lipid, for example, you get the 3D map of lipid. You look at protein, you can get a 3D map of protein, for example. And this is a thing that we would like to do a lot of work on. So you get two synchronized lasers and you send to the microscope, and you can do lipid, you can do protein type mapping in 3D. Right? So this is a really powerful technique. So we published the paper a couple of years ago, and the good news is that the technology has been commercialized by this company, and this is the first customer, I think, that they have University of Michigan. So they're using this technique to study brain cancer, right? And the last time when I talked to Chris, he said they have looked at over 1,000 patients already with this type of system. Okay, so that's my last slide. I would like to thank all of my group members, of the students who have done of the work that I showed today, and my collaborator, and then funding agencies as well, because they gave us the means and the resources to do the work. Thank you for your attention.